So let's talk about titration curves and what we can figure from them. Start with a weak acid, strong base titration. Obviously, we already know that the equivalence point is going to be above 7, and that is because of the presence of the conjugate base of that weak acid. But it is the point, regardless of what the pH is, it's defined as where acid and base are present in chemically equivalent amounts, meaning that if the equation calls for a 1-to-2 ratio of acid to base, then that's what you have at that point. Another point that we have to look at here is this region of buffering. And so where the pH is not changing a lot. Let's first talk about, though, why it is changing at the beginning. So this is a weak acid, strong base titration. We do have a sharp increase in pH, which means we have a sharp decrease in hydronium at the very beginning when we start adding the base. The reason for that, compared to a strong acid, strong base titration, where it just kind of goes very slowly at first, is because with a strong acid, like let's say HCl, there is lots and lots of hydronium for the added hydroxide to react with. With a weak acid, like acetic acid, let's say, there's not much hydronium, and if the hydroxide wipes out a lot of that hydronium in the beginning, the pH is going to rise sharply. But you do also, with a weak acid, have the unionized acid itself, HA, which the added hydroxide can then react with instead of reacting with any more hydronium, and so that's why the pH becomes pretty constant here during this region of buffering. Another important point to note is the midpoint, which is where we are halfway to the equivalence point. So if it's going to take 6 milliliters of base to neutralize the acid, 3 milliliters would be the midpoint. At that point, the pH, which in this case is 4, is equal to pKa, which is useful because if we have the pKa, we know that that is equal to the negative log of Ka, so the Ka would just be 10 to the negative pKa. So if we have a pKa of 4, then we have a Ka of 10 to the minus 4. So where does that come from? Why can we say that? It comes from what's called the Henderson-Hasselbalch equation, which you will get on the AP exam, which says the pH is equal to pKa plus the log of the ratio of concentrations of conjugate base and weak acid. Now this is true for any point along our titration curve, but the reason that the midpoint gives us pH equals pKa is because at the midpoint the log of A minus over HA is going to become 0. And the reason for that is because we have exactly the same amount of conjugate base as weak acid, and so the log of 1 over 1, or the log of 1, is 0, which means pH equals pKa plus 0, or pH equals pKa. So if you think about this, if we go back to our original equation, this is the weak acid and the hydroxide, the strong base. The initial concentration of the weak acid, let's just say 0.10 molar. And the initial concentration of its conjugate, of course, would be 0. But at the midpoint, or the half equivalence point, the HA would have gone down to 0.05, all right? And by definition, the A minus would have gone up to 0.05. So that's why we can say that the ratio of A minus over HA at the midpoint, or half equivalence point, is 1, and the log of 1 is 0, so pH equals pKa. All right, so here's an example from AP Classroom. This is from video 8.9, just kind of stole this. Multiple choice. Table to the right shows values of Ka for 4 weak acids. Which of the following pairs of chemical species, when combined in equimolar amounts, that's very important, results in a buffer with a pH closest to 7.5? So the equimolar amounts is important because that means that it's kind of like being at the midpoint of our titration. It's not really a titration, it's just a buffer solution. So it's a weak acid and its conjugate base. And so if we remember that the Henderson-Hasselbalch equation reduces to just pH equals pKa if the conjugate base and its weak acid are, in a 1-to-1 ratio, this becomes 0. So we're just looking for a pKa that will be 7.5. So if we just take the negative log of these values, that should give me, one of them should give me pretty close to 7.5. And you don't even need a calculator for this one because there's only one candidate. If we look at the exponent here, this being 10 to the minus 8, and the coefficient is not 1 exactly, so that means that the pH is going to be 7 point something. So that is a good guess, again, because of that Ka being in that range. All right, here is from Khan Academy. They have a pretty good little illustration here with the particle diagram. Determine the pH of the following buffer solution made from acetic acid and sodium acetate, and they're giving you the Ka of sodium acetate. Okay, so when we look at this, we're going to use the Henderson-Hasselbalch equation because what we're talking about here is the ratio of a weak acid and its conjugate base. It's saying it's a buffer solution, so it's not a titration, but it still uses the same equation and the same concepts. So if we go through and what we're going to do is simply know that the pKa is pretty easy to find, right? That's just going to be the negative log of the Ka, right? So negative log of 1.8 times 10 to the minus 5 plus the log of concentration of A minus over HA, which is just a ratio, so the units don't really matter. So the fact that I'm counting particles instead of molarity is fine, right? So my A minus would be the acetate ions. So those are the little bald guys with no hydrogen attached. So I've got 1, 2, 3, 4 of those. And it looks like I've got 1, 2, 3, 4, 5, 6 of the HAs. So it's just going to be the log of 4 over 6. And so the negative log of 1.8 times 10 to the negative 5 is going to be 4.74. And then I'm going to say plus the log of 4 over 6. But the log of 4 over 6, because it's less than 1, is going to give me a negative answer. So I'm really subtracting. So anytime you have less conjugate base and more of the weak acid, you're going to end up subtracting. So that's going to give me, in this case, negative 0.18, which is going to give me 4.56. Even though this is not a titration problem, it kind of makes sense in terms of where we are along a titration curve. If we were getting those acetate ions because we were adding a strong base and some hydroxide, we would be before the midpoint, right? Because we don't quite have as much conjugate base created yet. So we're not quite to the midpoint if we think about our previous weak acid strong base titration. And so the pH would be a little bit below whenever it's going to be at the midpoint, where pH equals pKa.